Welcome to another video about electronics. This time we're gonna go back to the basics and look into the capacitor, how it behaves, and in particular the RC low pass filter. So we're gonna do all this in LTSpice, and I'm gonna try to explain why this happens. So this is the circuit I have. So I have a pulse which goes from 0 to 1 volt. So it's either low or high, low at 0 or high at 1 volt. Next you have the resistor. This is 1K. And then you have the capacitor, 1 microfarad. So that's your typical RC low pass filter. And the important thing about it is that it's all governed by what's called the time constant. So here I'm putting some comments about important things about this. So the time constant R times C is the time it takes in seconds for the capacitor to charge or discharge by an amount of 63.3% or 63.2, depending on who you talk to. So in this case, RC is equal to 1K times 1 microfarad. That's 1 millisecond. 1 millisecond. So this means that C, the capacitor, charges to 63.3% of its full charge in 1 millisecond. And the same happens when it discharges. It's losing 63.3% of its charge in 1 millisecond. Well, this comment, this is going to be for the next LTSpice simulation. So let's just run this guy and see what happens. Okay, so let's look at the input. So this is your pulse. That's the high, 1 volt, and that's the low, 0 volt. And you can see that it's high during 10 milliseconds and it's low during 10 milliseconds, not counting the time it takes to fall and rise. But it doesn't really matter. So now let's look at the output. Okay, so let's explain a little bit what's happening. One of them. So let's say we are here. Okay, we are here. Right here. So here you are at 0. And the capacitor is fully discharged. So now the pulse goes to 1 volt. What's going to happen is that the capacitor is going to charge. And after 1 millisecond, which is about, I don't know, around here, it's going to be 63.3% charged. So that's your RC time constant about here. And that's 1 millisecond. Okay, this space divided by 10. And if nothing changes, it's just going to keep charging until it's fully charged, and the voltage at the capacitor is the same as the voltage of the pulse. So 1 volt. And it stays there. And here what happens is that the pulse goes to its low voltage, so it goes back to 0 volt. And the capacitor is going to discharge. And after 1 millisecond, which is about here, let's say, it's going to lose 63.3% of the charge, which is the RC time constant. So it's discharging, and then it's fully discharged here. And the voltage is 0. Another way to look at it is that so when the pulse is high, so this voltage is 1 volt, and V out is 0, the capacitor is going to charge because the potential here is higher than there. So it's going to, and the current is going to go from left to right. Now, when the capacitor is completely charged, so meaning that V out is 1 and the pulse changes state, and V in becomes 0, so V out is greater than V in, so the capacitor is going to discharge. There's no way around that. So it's just, so now the current is going to go the other way. It's going to go from right to left, so this way. So that's another way to look at it. But we can have a look at the current and see how it looks like. Okay, so this is the current that goes through the resistor. And let's focus on one cycle. So let's start, let's say, here. So here, the capacitor is starting to charge. And what's going to happen is that, so the red trace is the current. So the current is going to go max positive, positive being from left to right. So it's going to be max, and as the capacitor is charging, of course, the current is going to go down, down, down to 0. And 0, you have 0 microamp here, meaning that the capacitor is fully charged. Okay. Then the pulse is going to switch to its low voltage, 0. So now what's going to happen is that the capacitor is going to start discharging, and when the capacitor starts discharging, the current is going to be maximum in the opposite direction. So it's going to go from right to left, and it's going to be max there. And then as the capacitor is discharging, the current is going to go down, 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 down until it goes back to 0. And that repeats forever and ever. Okay, so we're going to move on, and let's read that third comment, which is going to segue into the next simulation. So to get rid of the pulse and only leave behind the DC level, in our case it's 0.5 volt, which is the average between 0 and 1. So that's basically the ultimate low-pass filter. It will only pass through the DC. Anything else is going to be removed. So what you do to achieve that, you simply increase the RC time constant so that the capacitor has no time to charge or discharge. Okay? So in our case, we are just going to change C. So I'm going to use 1 micro, 10 micro, 100 micro, I believe. And we're going to see the effect it has on the output voltage. Okay, so this is the next simulation that we're going to do. And of course, all those LTSpice files, I will put a link on how to get them in the description, if you're interested, of course. So here it's the same setup. We still have the pulse. We still have that resistor, and the only difference is the capacitor is now, it has a variable capacitance. Basically, we're using a parameter. We're going to be stepping through values of 1 micro, 10 microfarad, 100 microfarad, and see the effect it has. Other things of note. Here, that 0.001, this is to get rid of that time it takes for the pulse to rise or fall. So you avoid that slant. It's just cosmetic. It really doesn't matter that much. And the other thing I did is that I put an initial condition of 0.5 volt on the capacitor so that there's no transient, because otherwise if you start at 0, the capacitor voltage needs to ramp up to its average voltage, and the waveforms don't look as nice. So it's just you don't have to do that. If you put 0, you may want to do a simulation that lasts a bit longer to get out of the transient. Anyway, so let's run this thing. Okay, so V in, I'm going to show it just as a reference. Nothing has changed, but now you can see that there's no fall time or rise time. And this is the V out. So here you're going to see the 3 traces corresponding to 1 micro, 10 micro, 100 micro. Maybe I should have done this slightly differently. Let me get rid of the this trace so that I got some different colors. Okay, so the blue one is the one that we did before, so that's the 1 microfarad. The red one is 10 microfarad. And the, I don't know what color that is, turquoise, that's the 100 microfarad. And as you can see, the higher the RC time constant, the closer you get to a DC voltage. So at 100 microfarad, so that's your output voltage, and it's almost DC. Okay, so let's look at the red one just to see what happens. So here, right here, so the pulse is at 0. So now the capacitor is gonna charge. So here the capacitor is charging. But as you can see, it has no time to fully charge. Because now at this point, the pulse goes to 0 volt. So now he has to discharge. And it doesn't discharge fully, because the pulse changes state again to high, to 1 volt. And now it charges again. So if you push that to the extreme and you put 100 microfarad with that turquoise trace, the capacitor has no time to charge, no time to discharge. So you end up with a DC level corresponding to the average. Okay, so let's move on to a more practical case where you want to remove, like, let's say, noise from a audio sine wave, for instance. So let's forget about all this and let's open a new simulation file and look into this issue. Okay, so this is the last one, I promise. So this time it's slightly changed, but not by much. So here I have a sine wave, which is 1K in frequency. So it's like an audio signal. Amplitude is 0.5. So peak to peak is going to be 1. And then what I did is that I put on top of that slow moving sine wave, I put a fast moving sine wave of 100K hertz. And that kind of simulates noise. So it's in series. And the input, the V in is actually here. But the rest hasn't changed. So I put 1K, so that the resistor and the capacitor is going to be this time 100 nanofarad. So I use this value, just enough capacitance to get rid of the noise, basically. It's just trial and error. I mean, there are formulas for that, but I just do trial and error. So let's run this thing. So let's look at the input. Okay, and let's zoom on it. Let's see if I can just take this guy. Okay, so this is my slow moving sine wave, 1K hertz, and the one that's riding on it is the 100K hertz fast moving sine wave. It kind of simulates noise, but okay, now let's look at the output. Let's look at the output. So this is the output in blue, and as you can see, the noise has been removed. And what also happens, of course, is that you have a phase shift because of the capacitive reactance here due to the capacitor. So it's just a phase shift. It doesn't really matter when you do audio, you just have a phase shift. Okay, so I think I'm gonna stop here, and I hope that you have a better understanding of what a RC low pass filter does and why it does what it does. Just like a better understanding of it. And I would like to give a big thanks to LTSpice or Spice in general, because it really helps understanding when you can just simulate all kinds of circuits and play with it. I mean, that's the best way to learn electronics. Just simulate, and see what happens. All right, I'll see you around. Bye.